In this video, we will be doing the final part of Homework 1, Part C, and this time we are switching gears over to a CSTR, which is a continuously stirred tank reactor. And we are going to go ahead and derive the time-dependent material and energy balance equations of the tank described. So we have some operating conditions, parameters, values that are given to us. And later on in the video, we will code, solve, and plot the time-dependent concentration and temperature profiles for this reactor when the coolant temperature is increased. So this CSTR is a jacketed reactor. So I have actually gone ahead and drawn the diagram for us already and written down some of our givens right here. I'm going to go ahead and explain right here what is kind of going on in this diagram. So this is a tank, and it is jacketed. And in this example, our reaction is actually exothermic. That is why this change, this delta, the change in enthalpy of the reaction is negative, because in an exothermic reaction you are losing energy. So we have this losing energy to the surroundings. So we have this coolant actually inside this jacket, and we are cooling it down because it is exothermic. It's creating heat, and we don't want to exceed, a certain temperature in our tank. And we have a certain flow rate going in. This Ca right here is the concentration of A. So A is just, in this example, a part of the reaction. And we are tracking the concentration of A as it moves through this reaction in time. And we have a temperature, a given temperature going in as well. And because this is a CSTR, a continuously stirred tank reactor, it is perfectly mixed. So the importance of highlighting this is that the concentration of A in this tank, because it is perfectly mixed, is actually equal to the concentration of A coming out. These are not equal to the input concentration of A, but they are equal to each other. And the same thing goes for the temperature. So the concentration of A in the tank and the temperature in the tank is the same as the concentration of A and the temperature of the compound coming out of the tank. So I'm going to write down a few things some things we talked about. We know that it's perfectly mixed. We also know that this has a fixed volume, which was given to us. It is 100 liters. We also said this tank is jacketed. With some sort of cooling. As I said, this is an exothermic reaction because of the negative heat of reaction enthalpy. And I also almost forgot to mention that we know this is a first order reaction. So we know that the reaction rate, Ra, is equal to K times Ca. The Arrhenius equation says that this K value is equal to A times the exponential of EA over RT. And this A value was given to us by this K naught value right here. Essentially, if this value right here ended up being close to 1, this A is the largest value that K could possibly be. So that is why we call that K naught. And I think we have all of the basics written out there. So now we want to kind of get into the material balances. Here the material balances are easier to do than the energy balances, so we're going to start there. It's also always just a good idea to start off with the material balances. Our general equation that we kind of follow is that the accumulation, and we're talking about A, the accumulation of A equals in minus out plus generation minus consumption. And this would all be of A. So A in minus A out, etc. Because we are focusing on component A. So for material balances, what we really want to focus on is the change in the mass flow rate. We have the mass flow rate in minus the mass flow rate out. We know that the mass of an object or of anything is equal to its density times the volume. We also know that the mass flow rate is equal to the density times the velocity times the area, which is also another way of saying density times the volumetric flow rate, which is the velocity times the area. So we should have kilograms per second. So we'll check that out really quick. We know that density is in kilograms per length cubed. Meters per second, area meters squared. So our meters cancel. This is just a 1, so I'll ignore that. And so we have the kilograms per second. So from this, what we want to say is, as mass changes, this rho times volume over time, and then we take the rho times Q in minus the rho times Q out. We know, or we can, for this problem, we will assume that the density is constant. So I'm going to go ahead and pull the density out there. So we have dV over dt. And I'm going to go ahead and group those. As you can see, we can cancel out the density values. And so what we end up having is the change in volume over time should be equal to the flow rate in minus the flow rate out. As we said up here, we know that this tank is a fixed volume. We are given the volume as 100 liters. So here we can say this dV dt is actually equal to 0, which means Q in must equal Q out. So I'm actually going to go ahead and add that here just so we don't forget. So instead of looking at a mass balance, which was kind of what we did here, we want to do a mole balance, since we are looking at component A. So something we would like to look at is the change in volume times the concentration of A divided by dt. And actually, let me point out the units here. So we have meters cubed, Ca is the concentration of A, so that's in moles per liter. And then this dt is going to give us a per time. So we've got quite a few units there. It'll make sense a little bit later. We're going to set this equal to the volumetric flow rate times Ca in minus Ca. And that would be Ca naught. But what about the reaction? So what we have here is we have in, we have out, but we know that there can be a generation and or consumption term. In this reaction, A is actually being consumed, which we will see soon. But how do we visualize this consumption? We're going to subtract the volume times the concentration of A times its K value. And right here, we know that K equals K naught times E to the EA over RT. EA is the activation energy of this equation. We are not too concerned on finding that exact value because they gave us E over R, and this is EA. So they already gave us that number. And when we plug this into the code later on, that's where it's going to go. Like we said earlier, we know that the volume is constant, so we can pull that out of that fraction. We're going to go ahead and divide both sides by V so that we can get the change in concentration of A all on its own, so that we would be able to put this into code later. So we have Q over V times concentration of A in minus Ca naught, minus Ca naught times K. So this is our mole slash material balance right here. I do want to go ahead and make sure that the units look good. So we know that Ca is moles per liter. It's the concentration of A. And dt will add a time down there. Meters cubed per second divided by meters cubed. So we already see, divided by meters cubed, multiplied by, this would just be moles per liter. So here we have moles per liter times second, and we know that the units of K for a first order reaction are second to the -1, moles per liter. Okay, so they all match and give us moles per liter times second. So essentially this is saying how many moles per liter is A changing, the concentration of A, how much is it changing over time. Now that we have the material balance, we are going to want to do the energy balance. So in general, we know that the accumulation of energy in this tank should be equal to energy in minus energy out minus energy lost, energy lost due to heat transfer. And our heat transfer is actually given here. We are just using U as an overall heat transfer coefficient so that we don't really need to worry about too much of the specific details. And then, like I said before, this reaction is exothermic. So there's energy lost due to it being exothermic. So we are going to say that this accumulation term is the density times the volume times the heat capacity, which was given to us up here. We have the heat capacity. So we have rho times V Cp, and we're going to be looking at the change in temperature with time, because that is how this energy is flowing in and out, is generally through the temperature. And we're going to set that equal to the density times the volumetric flow rate. Like we said, the volumetric flow rate in equals the volumetric flow rate out for this problem, which makes things pretty simple. Multiply that by the heat capacity times T in minus T naught. So up here we have T in is the temperature of this mixture when it goes into the reactor, and T naught is after some amount of time it has been perfectly mixed and it comes out also at that temperature. We need to account for the energy lost due to heat transfer. So this is going to be UA times T minus TC, and this T is T naught. So that is the difference essentially between the temperature inside the tank versus the temperature in the jacket. This is going to cause heat transfer to occur, and this, like I said, is our overall heat transfer coefficient, multiplying that by the area. So that is the heat transfer, and then we are just missing the energy lost due to the reaction itself occurring. So we're actually going to go ahead, add the delta heat of reaction, multiply that by VKCA, kind of similar to what we did up here. And similar to what we did here, dividing by the volume, we're going to go ahead and divide all of it by rho VCP so that we can get this change in temperature with time on its own. So, all right, I'm going to skip ahead and I'm going to fill this out for you guys. Okay, so I've written that out. We have our energy balance. And similar to what I did before, I'm going to quickly check these units. So we know that this should be kelvins over seconds. So we have meters cubed per second over meters cubed times Kelvin. So we have Kelvin over seconds. Sorry, I'll try to distinguish between my kelvins and the K values for the reactions. It'll be hard to kind of distinguish. But there's that. This U times the area is in joules per minute times Kelvin. So we have joules per minute times Kelvin over kilograms per meter cubed times meter cubed times C is joules per gram times Kelvin. So I'm going to write kilogram just so we can cancel out what I wrote for the density. And again, this is just time. Oh yeah, okay. So I wrote out that. Forgot to include this Kelvin right here. So again, we have kelvins per some sort of time. So far it all works out. The heat of reaction is in joules per mole. Our K is in seconds to the -1. We have moles per liter for concentration. And we said that the heat capacity was joules per kilogram times Kelvin. Basically joules per weight times Kelvin. So let's go ahead and cancel out some of these values. I took a quick step away from this and realized I had a few errors. So I'm going to highlight those now. I was having issues with getting this to be in kelvins per second, but I neglected to realize that this liter term essentially is a volumetric term. Cancels there, joules cancel, moles cancel, kilograms cancel. So we get that correct one right there. Just right here, I was writing that down to make sure that I did that correctly. Other than that, another thing I would like to highlight in my equations, starting from the material balances, we're looking at the change with the concentration of A over time. We aren't necessarily specifically here looking at CA naught. So we just want CA. Now I'm going to fix that really quick, and then I'll come back and highlight over what I changed. It's the same here with this temperature. Okay, so there's a chance I left one of those unchanged, but just for reference, that should be T, just regular T and T. They should match. They should not be different. Same here, CA and CA. So our next step will be to put these two equations into code and simulate how these different parameters change with time. Specifically, we are going to be looking at the concentration and temperature profiles when the coolant temperature is increased from this initial 300 kelvins is going to be increased to 305 kelvins at time equals 0. So we're going to go ahead and get into the code now. So I actually went ahead and already put in a few things, and I'll run through kind of what I put into my code. So right here I imported something, a file from my course GitHub. Basically this has a lot of imports in it. It has a lot of data in it that I can pull from without having to type all of that out myself. So later on when I use anything from like IVP, anything like that, it's just going to pull straight from here. And this right here is a little update I had to do just to get these imports to work. And also, I went ahead and typed in these values. These are all of the given values that the problem gives us. I also wrote that down earlier. Very similar to parts A and B, we're going to start with defining the right-hand side for our differential equation. So we want to say define RHS, right-hand side, T vector, and we are looking at the concentration of A, temperature, and this is our vector. We also know that K, this is the Arrhenius equation. K equals A times E to the negative EA over RT. Our A is K naught, and we are multiplying this by the E to the negative ER over T, because we already defined this value right here is actually E over R. Next, we're going to be putting our material balance. So we determined that dCA is equal to the volumetric flow rate times the concentration of A in minus the concentration of A at any point in time, divided by V, minus K times CA. Secondly, we would like to put in our energy balance equation. So we have dT is equal to Q times the temperature in minus the temperature at any given moment divided by the volume minus UA. The U is our overall heat transfer coefficient. Then we have multiplied by the area times T minus TC. TC being the temperature in the jacket surrounding the tank itself. And let's see, divided by rho times the volume times the specific heat capacity plus our negative heat of reaction times K times CA, and then divide that by rho times the specific heat capacity. Return, we want dCA and dT. I'm going to go ahead and comment these out really quick. So since this simulation is in minutes, I'm going to do 10. Tplot equals numpy dot lin space 0 until t end let's just do, yeah, we'll do, that's fine, 1,000 equal partitions there. The results are simply integrate solve IVP. This equation looks a little bit different than we were doing before, just due to this import right here. But it does the same thing that our solve IVP did in parts A and B. Right hand side, from 0 until t end, our initial givens are CA naught and T naught. As always, this is our method, making sure I spell that correctly. Dense output equals true. Now we need to make sure that we are able to plot this. Make subplots. Let me just run this to make sure I'm not, okay, have some errors. Just gonna run it all and see what happens there. Okay, those errors went away, so we're good to keep going. Add scatter. So this is our plot for the concentration. We also want to add one. I'm just going to take that and see if that's what I want. We're going to add one for the temperature plot. Name it T, that looks good. Rows, columns, yep. So let's run this and see what it looks like. Okay, so I completely forgot to say that the concentration of A plot and the T plot are right there. Results, solve this T plot, and that should make our errors go away. Okay. So what we have here is this blue line represents the concentration of A over time. X-axis is time, y-axis is concentration. Notice it starts at 0.5 because our concentration of A in the tank initially was given to be 0.5. So obviously we can't get above 0.5. And as the reaction begins, the concentration of A decreases. In fact, it gets really close to 0 around like 0.6 seconds. So let's look at what happens to the temperature at 0.6 seconds. At 0.6 seconds, we are reaching our peak temperature, which makes sense. As the temperature increases, our reaction rate is also increasing. As the reaction rate increases, the concentration of A decreases because it is being consumed by the reaction. So when we get to this point, the temperature starts dipping back down again, and that is because the concentration of A is so low that it is not proceeding. And so you get these dips and valleys that are kind of opposing each other just because of the duality of the concentration of A and the temperature. Alright, so that was the final part for homework 1. We had part A looking at proportional controllers, part B looking at proportional and integral controllers, and part C we looked at the continuously stirred tank reactor balances. All included coding, and so yeah, stay tuned for homework 2, which I'm sure will be coming very soon.